I'm Dan Rockmore, chair of the Department of Mathematics here at Dartmouth and also director of the William H. Neukom Institute for Computational Science. And on behalf of the college and the Neukom Institute, I'd like to welcome you to this year's Spring Donohoe Colloquium, Mission Impossible, Constructing Charles Babbage's Analytical Engine, delivered by Professor Doron Swade of England's Portsmouth University. The Donohoe Colloquium is an ongoing series of public lectures aimed at increasing awareness of the many important and sometimes surprising places in which computational ideas appear. These lectures are made possible by a generous gift from David, Mickey, and Dan Donohoe in honor of Dan's graduation as a member of the class of 2006. The Donohoe Colloquium is a central piece of the larger mission of the Neukom Institute, whose aim is to support and integrate computational thinking and computational ideas throughout Dartmouth. So, no discussion of computation would be complete without considering the inventions that actually affect these processes. It is in this regard that Professor Swade speaks to us today. While the word computer derives from the Latin computare, which means to sum up, computers have evolved so far and so widely that for many of us, the connection to simple arithmetic is all but forgotten. Today, the name computer is perhaps better associated with the grand diversity of processes now produced by any digital device. It is something of an irony that the way in which we today use the word computer is in fact much closer to the original use of the word, as the name for any one of the legions of people who were employed to perform by hand and for hire significant and multi-step calculations for any of a variety of quantitative tasks. In some sense, the grand goal of computer science and computer engineering is to make future computers more like these original human computers. While simple calculating machines go back some 5,000 years to the abacus at least, it was not until the mid-19th century that we find the design of the kind of flexible or programmable device that might someday grow up to engender our own digital age. This was accomplished when the British mathematician and polymath Charles Babbage came up with plans for the Analytical Engine. The story of Babbage and his quest to build the Analytical Engine is, like any good tale, both of its time and timeless. When Babbage undertook his project, science was still largely the province of the amateur or the natural philosopher. Indeed, the word scientist had yet to be coined. Babbage was a great believer in the importance of intellectual and scientific breadth, today called interdisciplinarity. And Babbage's Analytical Engine project was actually never proceeded beyond the design phase, and his frequent complaints as to the unreasonable nature and short-sightedness of his local funding environment would undoubtedly resonate with many faculty members today. Luckily, Babbage has found a champion in today's speaker, Doron Swade, who is leading an effort to prove the viability of Babbage's 150-year-old design. It is an extraordinary project in the history of ideas that lies at the nexus of the sciences, engineering, computation, and the arts. The truly interdisciplinary nature of this project requires a certain breadth of interests and expertise. Professor Swade studied physics, electronics engineering, philosophy of science, machine intelligence, and history at various universities, including Cambridge University and University College, London. Doron is currently visiting professor in the history of computing at Portsmouth University and research fellow at Royal Holloway University of London. He is a former assistant director and head of collections at the Science Museum, London, where he was also senior curator of computing. He has published widely and is the author of several books and is especially well known as a leading authority on the life and work of Charles Babbage. In 2009, Professor Swade was made a member of the Order of the British Empire for, quote, services to the history of computing, unquote, of which the most notable was his leadership in the magnificent construction of the first complete Babbage calculating machine, the difference engine, built to original 19th century designs. His new and daring project is sure to prove to be at least equally amazing. Please join me in welcoming our Donohoe Colloquium speaker, Professor Doron Swade.
Dan, thanks very much for those generous comments. And thank you to Dartmouth, to the Neukom Institute, and to the Donohoe Colloquium for the opportunity of participating in this program. It really is a pleasure to be here. Thank you. I was struck by the inclusion in the aims of the Neukom Institute, the inclusion of a reference to expanding or extending computational ideas, computational thinking into general thinking. That is to take it outside the computational culture of the internal discipline of computing and look at its broader implications, or to see where these things provide models or relevance. And Babbage, polymath as he was with a huge range of interests, provides a huge number of his examples of instances in which computational culture actually spills over and affects history of ideas. So although I'll be concentrating to a large extent on the engines, the difference engines, the analytical engine, what I'll do is flag as we go along instances in which these computational models, these computational ideas actually have relevance way beyond computing itself. And perhaps that's less surprising in the 19th century, where polymathy was actually more widespread than it perhaps is now. So the story of Charles Babbage and his efforts to build these automatic machines in the 19th century is increasingly well known. What we have here is a mathematician, an accomplished mathematician at the age of 29 in 1821, conceiving of an automatic computing engine. And he devoted much of the rest of his life to the pursuit of this. He failed. So we have invention and failure, and in the context of Babbage, these two are almost invariably mentioned in the same sentence, invention and failure. He failed despite a blank check from government, independent personal wealth, decades of design and development, the social privileges of a gentleman of science, which gave him access to the highest echelons of British society, both in government and the aristocracy, and nonetheless he failed. Well, we built one of the engines, as Dan has mentioned, and what gives particular relevance and urgency to that construction, what revives interest in that, is this recent undertaking to try and build an analytical engine, which is 10 times bigger, vastly more sophisticated. And part of what I'll be focusing on addressing during the course of this evening is whether the mission impossible as a statement should have a question mark next to it, whether it's an ironic statement or actually whether it is possible to do this thing. Because as will become evident, what is involved, there are certain what are known politely as challenges. So what I propose to do is very briefly give a thumbnail biography of Babbage, and do this through iconography, do this through images, 4 images in the way he was represented in his own time. Secondly, describe the engines, describe what the ambitions and expectations for these engines were, and also to some extent how they work. And in the course of which I will describe the construction of Difference Engine 2, the first complete Babbage engine built to original designs. And finally then very briefly try and assess what the entailment is, what is entailed in attempting to build a machine that is at least 10 times as big. I mean, Difference Engine 2 took 17 years to build, and we reckon that, and that has 8,000 parts and weighs 5 tons. The analytical engine we estimate to have between 50 and 80,000 parts, and if these things are scalable, we're talking about a project that will take 170 years. So what I will do at the end is assess whether actually this is a realistic thing, or whether there's some what we might call assists, things that will brighten rather than darken our prospects. So if we just very briefly to give a kind of contextual outline of Babbage. This is Babbage in 1813, age 21, undergraduate at Cambridge. Those are miniatures that are in the possession of the family. And on the left is Georgiana, his fiancée, and on the right is Babbage. The resemblance to Napoleon is not accidental. Babbage, as a student, actually supported Napoleonic France, with whom England was still at war. The Napoleonic Wars ended in 1815, and Babbage, as a student, actually supported Napoleon. He defied his father, and in 1814 ran away. Well, he didn't elope, but he actually, in defiance of his father was a very wealthy banker, and who regarded it as imprudent for a young man to marry without means. And Babbage had no career, had no profession. He was an undergraduate. He was due to graduate the following year. Went off and married Georgiana despite his father. So already we have defiance, we have independence of mind, and we have to some extent the suggestion of radicalism. This is Babbage, man of science, esteemed by his peers. He is about age 53, mid-50s at this stage. It's an oil painting by Lawrence. Babbage was capable of incontinent savagery. He launched sarcastic public attacks against the scientific establishment for the mismanagement and poor governance of science in Britain, which he regarded as in decline and inferior to European science. And he succeeded in alienating most of the senior figures by launching personal attacks against them, including Sir Humphrey Davy. This was in 1830. He published Decline of Science in England. This is now already 1844. So by this stage, he's already partly rehabilitated and enjoying the esteem. He has an oil painting by Lawrence, a famous portraitist. And so by this stage, he's already, to some extent, redeemed. This is particularly interesting, daguerreotype by Claudet, because it is taken around the time that Babbage was designing Difference Engine 2. So we've actually got a photographic image of Babbage at the time he was designing his masterwork. This was a device, this was Babbage at the top of his game. He had already designed the Analytical Engine, which was vastly more demanding than his earlier Difference Engines, and realized that he could build with huge elegance, efficiency, and simplicity. Well, actually, it's complex, so it's comparatively simple. A much more efficient Difference Engine, and that's the machine we built. So this is Babbage at the top of his game. Spirited, beaten up, but still spirited and up for it still. Still with some anticipation, he hadn't entirely given up an expectation that one of his machines might still be built in his lifetime. This is Babbage with what I call his Beethoven look. This is 1860. He died in 1871. This is the last known portrait of Babbage, taken at the 4th Statistical Conference in London. And this is Babbage, professionally unfulfilled, self-perceived failure. He did not deliver an engine. He failed. And he measured his worth by his ability to demonstrate to his peers, through the delivery of a physical engine, his ideas. And to that extent, he failed. He refused public honors because he said the honor was for the engine, not for himself. And since he had failed to deliver one, he refused to accept it on his own behalf, as it were. Despite that, during his career, he ached for honors. He ached for honors. He drew up lists of comparisons of pensions and emoluments that his peers had received as dispensations from government and that he had been denied. So he had a strong sense of injustice, a strong sense of being overlooked. Yet, nonetheless, he preferred actually to remain, in some sense, obscure in his acknowledgement because of the lack of recognition of his engine. So this is Babbage. And his first biographer titled the biography The Irascible Genius. The Irascible Genius. And that perhaps that was 1963. And that is, if one's looking for a single signature characterization, a thumbnail characterization of Babbage, then Irascible Genius does the job pretty well. So what we have is a complex and colorful character. He authorized 6 full books, nearly 90 articles, on a massive range. Even by the standards of Victorian polymathy, this is a very, very wide range of interests. We're talking about a man who was proud, principled beyond reason. Principled beyond reason. He would attack people on grounds of principle, quite regardless of the political implications of so doing. He behaved as though being right entitled him to be rude. And this is, again, a characteristic that characterized much of his public conduct.
We all know people like that.
Nonetheless, he had great charm. He was a prized dinner guest. Mr. Babbage's coming to dinner was a triumph for any hostess. Yet he was capable of wounding abrasiveness. You can see this disconnection between the need. Schmoozing wasn't his strong suit. We could say. So politically, there was a huge ineptness. He didn't understand that having failed to build Difference Engine 1, it was more important to finish a machine that was not his latest design as a staging post in credibility in political terms than it was to try and sell his latest design to government, try and to prevail upon government to abandon huge investment in his earlier design and build his Analytical Engine. So you can see there's a political kind of ineptitude there, which came together with this boldness, this independence, and this pride, this huge pride. So much for Babbage. That's a kind of quick context of who Babbage was, and briefly the trajectory from an idealistic student into an eminent man of science, into a disillusioned and to some extent embittered embittered in older age. So, what were his engines about? What was he trying to do? What were his expectations? What triggered? What was the jumping off point for this whole thing? It's captured in a delightful vignette which occurred in 1821, where Charles Babbage and John Herschel, his great friend from Cambridge, the astronomer, are checking mathematical tables. Mathematical tables were calculated by hand in those days, as Dan said, by people called computers. And we have Babbage and Herschel checking them. So two sets of independent computers would do the same calculations independently without collaboration. And the idea is if these tallied, then you have a fairly high degree of confidence. There were instances of both groups making the same mistakes, but they're very rare. And so if they tallied exactly, you had a fairly high degree of confidence about the accuracy of the tables. And so Babbage and Herschel are sitting there checking these tables. One is reading out a result, the other one is checking it. And Babbage becomes increasingly agitated, and he clasps his hand to his head, as it were, and he says, "I wish to God these calculations had been executed by steam." And Peter Ackroyd, the novelist and historian, has said, "This is the most wonderful sentence of the 19th century." Because steam represented not only the infallibility of machinery, the unerring certainty of mechanical means, as Dionysius Lardner put it, but it was a metaphor for production. You could now produce tables on demand. And amateur astronomers were pressuring government, making thoroughgoing nuisance of themselves, trying to get the government to pressure the Greenwich Observatory to produce tables for the trajectory of new stars. And the reason they were sitting there doing these astronomical tables was to provide these tables. So here you could have tables on demand. You could turn the handle literally and metaphorically and produce tables at will for new functions. You didn't have to go through the huge procedure of their production. Tables, it should be said at that stage, were indispensable for science, for engineering, for navigation, particularly for navigation, for taxation, and for surveying. You were reliant. The only portable means of doing complex calculations beyond trivial arithmetic were through printed mathematical tables. So, what was involved in the production of printed mathematical? That's a set of logarithms, a piece of a page of logarithm from von Wegener, 1794. So that's what Babbage was trying to produce. Now, how was that produced? Firstly, manual calculation. Human beings sat there and did the calculation. Secondly, you then had to transcribe the results into lists to give to a typesetter. The typesetter would set each individual digit in loose type. So you took a piece of type for every single digit there, and to create the page. This is purely for dissemination. This is to communicate the tables elsewhere. You had to have a mechanical method of production. And then finally, verification. You had to check to see that the lists and the tables were correct. So it's calculation, transcription, typesetting, and verification. Now, Babbage's conception was a machine would eliminate all sources of error at a stroke. So it would have automatic typesetting built in. It would have a built-in printer, not only produce hard copy, inked hard copy, because that you would still have to transcribe. It also automatically produced stereotype plates. So the results were stereotyped. They were impressed on trays with soft material, either plaster of Paris, copper, papier mâché, to produce the mold for a printing plate. So you set the machine up, you entered the initial values, you turned the handle, and you got printed hard copy as a checking copy, and you got a printing plate out at the end to produce that. Now we'll say, well, okay, why spend staggering sums of money? He spent equivalent of, in today's terms, £100 million on the engine that he never completed. The argument of the day was there is no economic case for doing this. The experts of the day, George Biddle Airy, Astronomer Royal, Seelander in Sweden, Leverrier in France, all argued, or astronomers, all evaluated these Babbage machines and the Scheutz machines, Swedish machines built to Babbage's ideas, and said that there was no justification for doing it. Firstly, economically. If you took the same capital and used the interest to pay computers, it would be cheaper, firstly. Secondly, why do you need 30, 40, 50 digits of precision when you could only measure to 3 or 4 in those days? So these were people arguing there was no practical use and it was not economically ill-founded. So, so the point of that is that it was not universally agreed amongst experts of the day that there was any real utility for these machines, but that it was the jumping off point without question. So if we say, well, That doesn't seem too difficult a task, you imagine, to produce that by hand, to transcribe public. If you look at the page it comes from, you say, well, okay, even that is still doable without this huge investment. But if you look at the volume from which that came, you'll say, okay, I challenge you to have verified those numbers and tell me that you have some degree of confidence in the accuracy. Because unlike text, literary text, there is no intuitive way of knowing whether there's a spelling mistake. There's nothing that corresponds to a spelling mistake in this. And it's only now with computers where you can scan that in and verify the tables that you can actually resolve, through a piece of experimental history, the historical question, who was right? Was Airy right in saying tables are sufficiently accurate? You would get no additional advantage in building a machine purely to ensure the integrity of the tables. Or was Babbage right, and that these things were riddled, rather Babbage's protagonists, the advocates for the Babbage machines, of whether these things were riddled with errors or not. And now we're in a position, it's a project I've been trying to get a university to take up for the last 20 years, scan them in, check them out, and say, well, who was right? Wonderful. Combining science and history. Through experiment, you can resolve issues of dispute. To a large extent, the job's been done in Germany, where they've actually taken all the major rare book tables and evaluated them, scanned them, and verified them. And, right. So, 1821, Babbage is conceived as an engine that will eliminate. Now, Babbage did not assume that because the machine was mechanical, it was therefore immune from error. Because machines make mistakes, and there are oodles of examples of those. But what he did show, and he worked on the principle that because it was mechanical, he could, through control systems, locking systems, security systems, ensure that it was free of error. And I will show you examples of his security systems of how he ensured the digital integrity of his machines through a really ingenious device. And he was the first to do that, choosing a digital, discretized motion as a way of ensuring integrity and through control mechanisms. So, Babbage spends from 1821 to 1830, he spent about 10, 11 years designing difference engine number one. It's called a difference engine because of the mathematical principle on which it's based, which is the method of finite differences, and we won't go into that, but simply to say the beauty of the technique is that you can find the value of a polynomial expression, a mathematical expression, using addition only, whereas ordinarily you would require multiplication, division, subtraction, and addition to find the value of an equation. Here you can do it by addition only, and addition, a gear wheel with a value where rotation is proportional to value, linking with another gear wheel, and moving is an essential in adder. You're adding the number from one wheel to another wheel by allowing one to rotate the other. So addition is kind of quite easy, comparatively easy, compared to multiplication and division. Using gear wheels, multiplication and division was hugely difficult, accomplished in the analytical engine, but not for the differences. So the beauty of this was it allowed mechanics to get a grip on arithmetic. And in the course of trying to mechanize arithmetic, he was led from mechanized arithmetic to fully fledged digital computation with the analytical engine, which embodies almost every single logical feature of a modern digital computer, as we shall see. So, difference engine 1, I'm pointing to that as difference engine. That is 1/7 of the full-sized engine. This is 1/7 of the full-size. Now, it's probably the most celebrated icon in the prehistory of computing, this machine. This is 1/7 that is completed. It still exists. It works impeccably. It's on display at the Science Museum in London. It's operated by cranking a handle. So you crank that handle backwards and forwards 4 times to take the machine through a single cycle. You set the thing up initially by putting numbers from a pre-calculated table, which you do by hand, onto these columns. And what it does is add the number from the multi-digit number from this column into the next column, and the tabular result appears here. Every time you take the machine through a cycle, the next value of the table appears on the last column over there. So the point is, it's automatic. And the significance of it being automatic cannot be overstated. You crank the handle, you exert physical effort, and you get, for the first time in history, a result which you could otherwise get only by thinking. For the first time in history, you exert physical effort, and you get a result that you would otherwise get by thinking. And so you have the first transference of human intelligence to machine. Looking at it the other way around, you have the first ingression of machinery into psychology, because the significance of this was not lost on Babbage and his contemporaries. Harry Wilmot Buxton said, the wondrous pulp and fibre of the brain has been replaced by brass and iron. He, Babbage, has taught wheelwork to think. Lady Byron, Ada Lovelace's mother, in 1833 wrote in a diary, "Last week we saw the thinking machine, for such it seems." Now, Harry Wilmot Buxton says, wondrous pulp and fibre brain, he, Babbage, taught wheelwork to think, and he adds, or to do the office of thought. So they were not saying minds are computational. What they were saying is, you have for the first time a machine capable of mind-like activity. It was doing something that up to that point. Now, the significance of this is monumental. You have, if you like, in a broader context, the idea of the industrial metaphor of production, the model of industrial production being extended from thought, from thing to thought, from matter to mind, from physical to mental. The Industrial Revolution was to do with replacement of physical labor, physical work, and here you have a machine producing mental work. So this was the first artificial intelligence machine. If you like, that's the beginning. And you had to have, to some extent, machine autonomy. You had to have some element of autonomy in the machine before you can begin to have automatic computation and begin to have machine intelligence. So this machine is hugely significant historically. It is significant in other respects. And this is an example of what I mentioned early on about how a computational idea is spilling over and having an impact on the history of ideas. We have here an example of an artifact influencing the history of ideas. Here we have Babbage, the difference engine, the 1/7 complete. That's Ada Lovelace, and standing next to him in the dark is John Herschel. The reason that the quality of that photograph is poor is because digital photography wasn't very developed in the 19th century. That is a BBC reconstruction of Babbage demonstrating his theory of miracles. So here we have a computational model, and we have Babbage actually entering a debate and having huge influence, significant influence on geologists, on pre-Darwinian evolutionists, about discontinuities in nature. And this is how he addresses an issue and reconciles a hugely difficult issue in the 1830s, which was, how do you reconcile a belief in a God with rational thought and science? Because an earthquake occurs if a deity is used as the causal account for the earthquake, there is no difficulty. So what they were struggling with was this. You had millennia of geophysical stability and suddenly an earthquake. You had stability in relation to species, and suddenly you had the occurrence of a new species without. Now, science espouses material cause. So the question was, in the absence of a miracle, how would science, if it was competing with religion for an account of the world, give an account of something discontinuous? So Babbage in his soirees, if you were part of the glitterati or intelligentsia of London, you went to Babbage's soirees on Saturday. And there he had his engine, and this was taken at one of his soirees with a digital camera in 1833. One of his soirees demonstrating his theory of miracles. And what he would do is he'd program the machine to do something quite banal, increment by 2. So every time you crank the handle, the number at the end would increment by 2. So it went 2, 4, 6, 8, and so on. And, he would play with his visitors and say, well, what do you think the next number's going to be? And they'd say, is that terrific? And, he'd keep doing this. And eventually it got quite boring, and they'd think, well, this is actually banal or something. And suddenly, without intervention by Babbage at all, the machine would jump from what it's supposed to be to, say, 119. And, oh, Babbage, you've broken it, they would say. And then he would deliver his argument. And he'd said, you see, to you, the observer, this discontinuity is a violation of law. And the law is increment by 2. But for you, this is a violation because it's not increment by 2. But I programmed this machine that after 100 iterations, it would jump by 119. So to me, the programmer, this is not a violation of law. This is a manifestation of a higher law, known to me, but not to you. By analogy, miracles in nature are not violations of natural law, but manifestations of higher law, known to the deity, but not to us. And he allowed you, therefore, to be both a believer and a scientist and reconcile this progressive tension. So for Babbage, God was a programmer, and I thought those of you in the software industry may be flattered to know that. I mentioned that was 1/7 of the engine. Right, these are decimal digital machines, right? They work in decimal, not in binary, and they're digital. They're digital because motion is discretized. That is only fixed. So that's a gear wheel. It represents a value. So it's 1, 2, 3, 4, with each tooth representing a number. And so if you want to represent 2.5, the wheel doesn't sit between 2 and 3. You've got a wheel with 2 and a wheel with 5 on it. It's digital in that sense, but it's digital in the sense that only discrete integer numbers are legitimate and valid, logically valid. Now, the problem is that a gear wheel is an inherently analog device. All the transitional stages between 1 and 2 are physically viable, unlike a flip-flop, which has a threshold, a switching threshold, where if it's exceeded, it suddenly flips to another state. So unlike electronic thing, Babbage was dealing with inherently analog logic, which he then had to turn into digital control. He did this through using control mechanisms. Now here we see, this is top of the difference engine opened up in a little model that was built from parts made for the first difference engine. And you can see these semicircular stubs there, and you've got a sprung roller. You can see the spring there, and that roller on that lever is sprung and presses between the things. I can blow that up a bit. So there we can see the roller. Right, so as this tries to turn, there's resistance. So you can see that the dwell angle on the top of that thing is not sufficiently decisive, not sufficiently sharp to cause a decisive switch. But you can see the beginnings of an attempt to digitize motion, to discretize the motion, so that although it's still probably stable there, a small displacement will jump it into the next thing. So that's one of the earliest examples of Babbage's attempt to discretize, to turn an inherently analog component into a digital discretized thing. Now, there are much more sophisticated examples of how he did this, and we'll see an example. I'll show you a video of one of them actually operating later, where he uses a wedge which drives, and it's absolutely, the point of the wedge is a line, and the switchover is absolutely decisive. Right, I mentioned that it was 1/7 of the engine. That's the 1830 plan of difference engine 1. A precision of 16 digits, so it goes units, tens, hundreds, thousands, da-da-da-da-dum. So it's a 16-digit number there, which gets added to the column alongside it, and the tabular value appears over here. That's a printing mechanism. You can see it runs on tracks and rails. There are wheels on rails, so it's the first portable computer. It's between 8 and 10 foot high. It weighs well in excess of 5 tons. But it's portable. I mean, it precedes Osborne and all those other. It doesn't have a carrying handle, though. So you can see, firstly, we're talking about a quantum leap in physical scale and logical complexity in relation to what had gone before, which were little desktop calculators of dubious reliability and limited precision. And the point is they were not automatic. The algorithm was still in the human. The algorithm had to do the dials, operate the stylus, move the carriage. The algorithm was in the human still. Over here, we've got the beginnings of the first time the algorithmic instruction is actually being transferred to the machine. Right, we've been 8 to 10 feet high, 25,000 parts Babbage had made. In 11 years, his engineer, Joseph Clement, had made 12,000 parts, 12,500 parts, most of which got melted down for scrap subsequently. There are about 2,000 parts in the 1/7 full size. And these were some of the highest precision parts made in the 1820s. It's a kind of metrological standard. If you want to know how precisely could an engineer have made a part, then you take measurements from the difference engine 1. Okay, what I'm going to do, I'm aware that there's some people who may be technically well versed, and there are others that are not. So I'm going to read some of the logical features that are embodied explicitly. So these are not suggestive hints. These are logical circuit and system functions that are embodied in this engine explicitly in the detail of the mechanical design. So I'll rattle them off. They may mean more to some than to others. Firstly, parallel operation, non-destructive addition. You recover the addend after the addition. Microprogramming. It automatically executes a number of minor instructions, minor functions in order to execute a larger one. Pipelining, overlapped simultaneous functioning. These are modern terms with strong affinities to the logic there. Pulse shaping, that is cleaning up a degraded transition to ensure digital integrity. Binary latching, That's one word, storage, one bit storage, polling, sequence interrogation of a series of logical states. You poll the thing to find out what's going on. Input, output, there was manual input, printed and stereotyped output, and a Schmidt trigger, a bounce catcher, when the thing bounced and you had to stop it once it crossed the threshold. Now, I mentioned also that many of Babbage's ideas spill out beyond computation. We have now a very bright guy, a mathematician, who for the first time has a machine which can execute computational process. And it's curious what his speculations about this were. Firstly, he saw for the first time computation as a systematic method of solution. The way you solved equations before is you did analytic solutions, and abstract formalism, generalization, was prized. Computation was regarded as inferior because it was like arithmetic. Arithmetic was rather inferior to. So you can see there's already a kind of prejudice that Babbage was aware of against computation as systematic method of solution. But he's got a of calculation as, now he's talking about computation as systematic method of solution. That if you have an expression for which you do not have an analytic solution, you can now find solutions to this equation by computing them. You set the machine up, you crank the handle, and you crank until you find a solution. So the idea of computation as systematic method of solution, which elevates it, if you like, from the mundanity and banality of arithmetic, the inferior status of that arithmetic had in that culture, was very evident. And he says this is not in conformity with the tastes of the time. He was aware that there was a prejudice against computation as a systematic method, even though solution by computation was actually more systematic than analytic solutions. There was no systematic way of finding the solution to the equation. You had to manipulate until it had a form for which there was a known solution, which is one way. Trial and error, regarded as deeply inelegant by mathematicians. So curiously, what is regarded as inferior is more systematic than was the accepted methods. So you want to find the solution of equation, you set the machine up, you crank the handle, and a solution of the equation is when the independent variable, the value of the independent variable, which drives the equation to zero. So solution computationally is equivalent to the tabular value being all zero. Now you can detect that mechanically. So he's got a bell that rings in the difference engine, which warns the operator that a solution has been found. Or if the value goes through zero, if there's a sign change in the value when it goes through zero, it will ring a bell and stop. But Babbage also incorporated automatic halting mechanisms that would automatically detect the all zero situation. So you entered initial values into the machine, you cranked the handle, and the machine would stop when it found the first solution. If there were multiple roots, you would carry on cranking until another one. If there were no roots, you would carry on indefinitely. Now, anyone who knows about Alan Turing, who used the halting criteria to resolve the issue of decidability, you've got Babbage talking about the machine halting as a criterion of finding a solution, of solvability. So you have rather extraordinary pre-echoes here. And so Babbage was the first person in a position to consider what the implications of a mechanical process, which are a definite method, mechanical process, are terms that Turing actually used. So it's curious that two people, mathematicians, who thought this systematically. Right, he also saw the machine as having heuristic value. It could suggest series for which there was no... You could find the value of a series for which there was no general expression, which is another thing, and also heuristic value. The machine would actually suggest series for which there was computational rule, but no analytical formula. So he anticipated all things. He also anticipated that there would be a new branch of mathematics called numerical analysis that would be devoted to manipulating expressions for the purposes of machine computation in the most efficient possible way. And he uses an example where he has an expression which requires 35 multiplications and 6 additions, and he manipulates the expression to something mathematically identical, and he says you can do this with five multiplications and 1 addition. And he uses that as an example of how you need a branch of mathematics that would optimize the ability of a machine to do the computation. The project failed. In 1833, the thing was abandoned. His engineer walked out. Circumstances are very complex. They involve an unresolved dispute which spiraled out of control with his engineer, Joseph Clement, for compensation for moving his workshop closer to Babbage's house. Babbage regarded himself as the master, and Joseph Clement, his engineer, was the servant. And the expectation was that servants would obey masters. And Clement was quite intransigent about this, and within his rights demanded £600 compensation to move his workshop because he would lose trade and all the rest of it. Unresolved, both actually stood their ground, and the relationship was never repaired. The engine was abandoned. Now, during this period of the dispute, which lasted many, many months, possibly over 18 months, Babbage was deprived of his drawings and his parts. And in this enforced break from the nuts and bolts of construction, he began to go back to his original ideas, and that's the point at which, 1834, he conceived of his analytical engine. Okay, the difference engine is a calculator. It crunches numbers the only way it knows how. You put numbers in, you turn the handle, it's all it can do. It's not a general purpose calculator. You can't do ordinary multiplication, ordinary division, all the rest of it. It's exactly what we would call a calculator. It has a fixed algorithm, and it does everything according to that, according to the way the wheelwork is set up. The analytical engine involves, again, a quantum leap in physical scale and logical complexity, because here we have the conception of a general purpose computing machine, conceived the beginnings of the glimmers in 1834, made huge and massive progress by 1836. By 1838, he had a kind of plan, and the plan we're going to look at is, if you like, the mature version of his middle plans. So here we go. That is Plan 25, 1840. To give you some idea of the physical scale, the diameter of these central wheels is 5.5 feet. Each of these circles is looking at a column of figure wheels from the top. So each of these circles is a column of figure wheels, 40 deep. These central wheels are toothed wheels, 5.5 feet in diameter, with teeth on them, and they're 40 deep too, and they are the internal bus. So let's first look. That's the mill. That would correspond to the central processing unit, and this is the memory, what he called the store. We call it memory, he called it the store. So that's where the data was kept. So firstly, you see the separation of mill and store, of CPU and memory, which is a feature of the von Neumann architecture, which dominated computer design since 1945, separation of store and mill. These are racks. Now, a rack is a thin slat with teeth all around the edges, and that is a bus. So that's 40 deep. Every wheel is connected to every other wheel by this toothed rack, and you can transfer any data from any column to another column using these racks into the buffer stores and into the mill. So there's a fetch-execute cycle, which is another piece of von Neumann architecture, which fetches the data from the store, takes it to the mill, processes it, and returns it back to the store. So the internal architecture is, you'd say, pretty modern. The physical scale of this is rather extraordinary. The store can extend within practical limits indefinitely. It's a linear thing goes on. There's 17 what he calls, the things called V, what he calls variables. We'd call them registers now. So they are 40-digit registers, 30, 40-digit registers. Now there's 17 shown here. From here to there is 18 feet. Now the entry-level machine, that's got 17 registers. The entry-level machine had 100 registers, and he talks with machines for 1,000 registers. So we're talking about a machine that is 15 foot high, 8 foot across here, and the entry-level machine will be 45 foot long. So when I say this is a quantum leap in logical conception and physical scale, you're talking about something of huge complexity, which we'll explore very briefly now. But the physical scale of this is just utterly monumental. Morris Wilks, Professor Sir Morris Wilks of EDSAC fame, person who in the 1950s built the first post-war electronic workable post-war stored program computing in Cambridge, was one of the early people to evaluate Babbage's standing as a computer pioneer, described this as vision verging on genius. Anyone who knows Morris would hesitate to call anyone else a genius, but this was vision verging on genius, and I think that's a very, very extraordinary tribute from someone of Wilkes's standing, because he understood perhaps more than anyone at the point at which he evaluated this, what the implications of Babbage's accomplishments were. The rationale for centralizing the mill was interesting. He was saying processing hardware is very expensive, so don't distribute it. Centralize it and bring the data to it. Exactly what we do now. And he's very explicit about it. He's very, very clear about why it is he centralized the processing power. It's operated by, well, yeah. Right, I'll go again for those who are into computer science or circuit system design. I'll just read a bunch of features of this machine without bothering to explain. I'll go back and explain one or two of them. Firstly, it's programmable using punched cards. There's a separation of the store and mull, which we've mentioned. It has serial operation with the fetch-execute cycle. It has conditional control, so it's capable of if-then statements, which you need for multiplication and division. Capable of iterative looping, can repeat the same sequence of operations a predetermined number of times. It's got built-in microprogramming, which we'll explore very briefly. Pipelining again. Buffering. You take a number from the store and you put it in the ingress access over there, so it's stored in the buffer. The mill processes it and returns it to the egress access, which is there. So you've got a system of buffering, so it isn't just direct addressing. It has anticipating carriage, which is a form of carry look-ahead. It has an internal repertoire of automatic instructions. Multiplication, division, subtraction, addition is built in as a repertoire, as the internal repertoire. Up to 50-digit registers with double precision results, so up to 100 digits in the output. It's capable of parallel processing. It has multiple processors. It has 3 barrels. There, and there. All of which can operate at the same time. So you split the problem between 3 sets of processors. So, I mean, this is pretty advanced stuff. Punch card input of data and instructions. The outputs are printed, stereotyped, punch cards or graph plotter, or run on a curve plotter. It's a fixed point decimal digital machine. It uses sign and magnitude representation of numbers. Negative numbers are used handing tens complements. And we see here with the fetch execute and the separation of store and mull, the central input and output, the central features of von Neumann architecture. Right, punch cards. That's an example of a set of operation cards, which are instruction cards. Those are variable cards which tell you where in the store to place a number. So it tells you the location in store that a number is to place. The operation cards tell you exactly as you would now an instruction, add this, subtract it from that, multiply it by that, and so on. And these are in a fanfold form, and in Turing's terms, you can extend them to any practical, within the limits of what's practical, you can extend this indefinitely. Right, there is an example of Babbage's card reader. It's a prism, and that's reading variable cards. And what happens is, so there's a box full of them. That's the fanfold stock of cards. And what happens is this turns each cycle, and each cycle it turns and moves forward. That whole apparatus moves forward and activates these rods depending on whether there is or is not a hole in the card. That is how the activation is done. And so each cycle, this thing automatically cycles through. And you can begin to get an idea of what his drawings looked like. There's a barrel, which we'll look at there. There's a rack. That's looking end on a rack. So you can see there's 3 sets of teeth, and that is the thing that runs the full depth of the store. Interestingly, that more has been built of the analytical engine in Meccano than anywhere else. The last thing built for the analytical engine was a 4-function calculator built by Babbage's son, completed in 1910. It works, but not without error. And there's an extraordinary man, Tim Robinson, in California, who's built the difference engine 1, difference engine 2 out of Meccano, and is now building the analytical engine. So that is a card reader built by Tim Robinson. You can see the rods. Those are the rods which get pressed or not pressed, depending or not on whether there is a hole in the card. So that is how the activation of the higher level control worked. Barrels. I mentioned barrels. Okay. We have here a linear form of store, right? It goes on indefinitely. But in 1837, this is an 1840s drawing. In 1837, this was a circular arrangement, and you can see that the store is limited. Everything is around the circular wheels, and the store is limited by what you can fit around the circumference. So you can see an automatic progression. Now, there are 3 stages in his plans, early, middle, and late. That's the end of the early stage. The ones I've shown you is the mature side of the middle stage. The version we're building is Plan 28, which is the 3rd stage, which is even more elegant than the one I've described. But this is the Plan 25 is the most complete and illustrative of the drawings. These cards are quite huge. That's 26, 28 inches long, the variable and operation cards. And the variable and number cards are data cards, and the instruction cards are 7.5 inches long. So these cards are quite big. These are the barrels, and perhaps since I've been spending too much time on things that I shouldn't be, we should skip it. But that's a barrel, and you can see that there's a stud, and the whole barrel moves forward. The barrel is the microprogram. The barrel is the internal microprogram of the machine. So it's a barrel. It's like a barrel organ. So there's studs there. If the stud is present, this whole barrel, you can see the dotted lines. If the whole thing moves forward and either activates or does not activate one of these rods, depending on whether there's a stud present or not. And then it automatically retreats and then is advanced to the next stage depending on these other wheels here. Now those other wheels are controlled by the existing word. So each word instructs the barrel where the next instruction is by these sectors. So you can see there's a 1, there's a 2, and there's a 4. And they've got 1 tooth on it, and that's got 2 teeth, and that's 4 teeth. So that advances the barrel from one word, either 1, 2, or combinations of those, depending on what conditions are satisfied or not satisfied. You also include conditionals in that, and there's also multiple branching, so you can have multiple conditionals. Here's a conditional. If you get a running up, which is a sign change from the top of a register, then you will add another turn by lifting that sector wheel, or not, depending on whether it was running up. Here there's a condition that will take account of pre-existing states. So you can see there's a little slug there. If you withdraw that arm, there's a gap between the stud and the rod. And if that moves forward, it doesn't act. But if that rod is forward, then that fills that gap, and when the next time... So that'll be a pre-existing. So a condition arises, the rod moves forward, but the stud in the wheel, that it may be 5 instructions before that is actually interrogated. That is then polled, and a condition will result from pre-existing state. And these are all operate together. Now, you can work combinations of these because the phasing of these sectors operating is all different. So if they happen at different times, you can add anything from 1 to 7 moves. Now, that's a simplified version. You can have words, so that's a word in the vertical, if you like. It's a single computer word in the vertical, up to 50 high and 100 on any given barrel. And there are 3 barrels operating simultaneously as multiple processors. So, if that didn't mean a whole lot, we can actually just summarize by saying, when we call Babbage a computer, the first computer pioneer, it's not a casual tribute. This is not, these are not suggested hints. This is not a backwards projection from our own age. These features are explicit in the detail of Babbage's work. And that's a drawing by Alan Bromley, who sadly passed away in 2002. He was the person who first cracked these drawings. And that's probably one of the few illustrations which describe what it does. Babbage, that's a piece of the Analytical Engine under construction at the time of Babbage's death in 1871. That was all that was ever built. You can see the racks. Oops, there's a little printing press over there. And it was an experimental thing which it's questionable whether that ever worked. This is Ada Lovelace. And Ada Lovelace has a very interesting part to play in the Babbage story, because it was Lovelace, not Babbage, actually who understood the implications of what computing, as distinct from computation, meant. It was Lovelace who saw, in ways that Babbage did not, that number could represent entity other than quantity. A number could represent a letter of the alphabet or a note of music. Babbage always saw his machines bound by number or by mathematics. The most general form of his machine he saw as an algebra machine, something that can manipulate a symbol independently of the value of that symbol. But the machine can't do algebra. The machine is an arithmetic mathematical machine. He's got algebraic addition, and he designed a printer. There's sketches for a printer. He became intrigued by how do you elevate the symbol to get it above the horizontal line, and how do you lower it? So he had a way of actually controlling this. So he clearly had it in mind that the machine would produce mathematical algebraic notation. And Lovelace writes, 1843, the only published paper she did. Lovelace, I'm assuming everyone knows Lovelace. Lovelace was Byron's daughter, who Babbage met in 1833 when Babbage was 42 and Ada was 16. And Babbage and Ada sort of got it. She got it in ways that even Babbage didn't get it, and wrote in 1843 a famous paper, Sketch of the Analytical Engine, which is the most comprehensive and insightful, that captures the most insightful thinking about the Analytical Engine at the time. Hugely reliant and derivative of Babbage's work in all technical senses. But in this, there is Lovelace talking about the power of computers, the vision that the power of computers lies in taking representations from the world, putting them in numerically represented in the machine, and that the machine can manipulate symbols according to rules, And then you can start saying things about the world by mapping back the representations onto the entities that they're representing. And she saw that more clearly than Babbage ever did, that this was why this machine was significant. And this isn't, again, a casual thing in a footnote. This is Lovelace thumping the table, saying, it is this that is important about this machine. This machine is in a different category. It's a different in kind from anything that's gone before, because it is able to do this representation, the untethering of representation from thing and the manipulation of the representation according to logical as distinct from physical rule. And she had this vision in ways Babbage nowhere in his published writing writes in this way. And Lovelace uniquely does that. Now, there's a lot of mythology about Lovelace. She's fated and celebrated for four things. She was the first computer programmer. The programming language Ada was named after her. She had an influential. Had a positive influential effect on Babbage in the conception of the analytical engine. She was a mathematical genius, and she was a prophet of the computer age. The first three have absolutely no foundation in any form of historical evidence. The chronology just contradicts them entirely. All the examples she gives for her first program, the question of her being the first program is understandable but wrong. She was the first to publish a program, or something that we recognize as a program, as a stepwise sequence of operations, the notion of an algorithm. But the example was done for Turin in 1840 by Babbage. So none of the three claims, mathematical genius, first programmer, and influence on the analytical engine, stand up at all. But the prophet of the computer age, absolutely, in ways that actually, so not only is she deserved of the celebration she receives, she's more deserved than she actually is, because she's usually celebrated for reasons which actually are historically ill-founded. So that's my take on Ada Lovelace. We've arrived at Difference Engine 2, and I realize that we don't have a whole lot of time. Difference Engine 2 is the one we built. So Babbage he conceives of the analytical engine 1834. He gets a glimmer of it. Works with huge intensity till 1836, 1838. Middle plan, later plan. His late plans in 1846, Plan 28, which is even more evolved than this, but more to do with refinements than it is. He used half-zero addition and various other things. Refinements rather than big logical architectural breakthroughs, which is why it's useful to look at the plan I looked at, which is the 1840 plan. 1846, he stops, and he realizes he's now at the top of his game. He realizes he can build an elegant difference engine, three times more efficient, 1/3 the number of parts from difference engine 1. So this is like his masterpiece. He produced no experimental pieces because he conceived of it all entirely. Difference engine 2 is a hugely elegant, sophisticated difference engine. It has 8,000 parts compared to the 25,000 parts of difference engine 1. It is 11 foot long. It is 7 foot high. It weighs 5 tons. It will calculate and tabulate any seventh-order polynomial to 31 decimal places, is what it does. So you enter the initial values on these columns of figure wheels, you turn the handle, there's the microprogram in the cam stack, and out here is the output apparatus, which prints in hard copy on a inked print roll and stereotypes plates of 30-digit results. And I'll show you examples of those. That's the machine we built. It took 17 years, as I mentioned, although it actually took, if you had a kit of parts of 8,000 parts and assembled it, would take you 3 years to fettle it, to do it all. The 17 years was what might be called politics or life. It's prevailing upon people, it's getting money, it's producing drawings. Babbage left 20 drawings. It's the most complete design he ever did. He left 20 complete drawings. And those you can see that this defines the machine completely, but there's insufficient information to give a drawing like that for manufacturing to a machine shop. So we translated those to 168 drawings, where every single of the 8,000 parts is specified completely. And I'll show you an example of just how much information that requires. So that's the engine standing on display in South Kensington. And that's an elevation of the engine. You can see its huge similarity to similarity, it should be identical to the drawing because it is built to those designs. Okay, numbers are stored in figure wheels. They're 10 decades, 0 to 9, 4 times over to get the wheel about 5 inches across. There are 230-odd wheels in the machine. They are in columns, so you've got units at the bottom, tens, hundreds, thousands. So 30-digit number is represented there with one wheel for each digit. And what the machine does, that's the back of the engine. What the machine does is add the 7th difference. So it adds a 30-digit number, 31-digit number in that column, to that column, to that column, so on, until the tabular value appears here. It's automatically transferred to the printer and prints the results automatically with no overhead. The printing happens in parallel with the computation. If it just added this number to this number, and then this number to that number, only 2 columns out of 8 columns would be in use at any one time. And Babbage thought it was pretty inefficient. So he did what's called pipelining. He adds all the odd axes. He splits the cycle in 2, adds all the odd axes, that's axis 1, 3, 5, 7, 9, 1, 3, 5, 7, to all the even axes in the first half cycle, all the evens to the odds in the second half cycle, and in that way the machine is used fully, which means you can extend this indefinitely to 15, 20 orders of difference without increasing the calculating cycle time. So this was pretty sophisticated stuff. Right. At the end there, I said there was a printer, which does, let's jump ahead again. Okay, that's an example of the most intricate part, which is a carry arm. That's a carry lever, bronze. And you can see how much information you need. That's a modern piece part drawing with the piece on it. And there are over 200 of those in the machine. And you can see the kind of manufacturing issues involved here. That's the most intricate, most delicate part. And so you had to take those schematic drawings and make 8,000 of these in order to give it to a machine shop to manufacture. Okay, we spoke about the printer, which is this apparatus over here, and that's the printer built. Now it's programmable. It's programmable. You can alter the format of the information on the page. So you can change the number of columns, anything from 1 to 4. It's got variable line height, variable margin widths. It will leave blanks between groups of lines for ease of reading. It will print in 2 fonts simultaneously and alter the line height automatically. And if you can print line to line. Okay, that's printing column to column, so it's going column to column, and then automatically line wraps. Or you can program it to print column to column, line to line down the page, and it'll automatically column wrap. And it does that automatically. The printer then halts the machine at the end of the thing. Each piece of information, every time the machine calculates the next result, it destroys the previous one. So if the machine overruns and you haven't printed the result, you've got to start the calculation all over. So it's imperative that the machine halts automatically at the end of the stage so you can replenish the trays for a new page. And it does this automatically. That's built into the printer apparatus. And I'll show you the notation about how that is done. That is an experimental impression of a stereotype plate done from this machine in plaster of Paris. So we've actually did some experiments to see does this thing actually work, and that's what we get out of it. That's a plan view of the printer. You can see that's the large font, that's a small font. And so these are rods operating from the same print wheels, which actually allow you to produce a smaller font. The reason I'm showing you this is to look at this table on the side here. Now, Babbage invented a language. Okay, we have systems of unprecedented complexity here. Nothing had been designed of this scale at that time. And he developed what we would now call a hardware description language to actually not only optimize the design, but to specify the design. So you could see redundancies automatically, and he could actually specify the machine using a language, an idiosyncratic language that he devised called his mechanical notation. It's a system of signs that allow you to specify every part, the category of part, its motion, whether continuous, whether discontinuous, whether circular, whether linear, what other parts any given part is connected to, whether it's a driving point or a driven point, and so on. So he developed this notation, and that's an example. There's a tabular form. There are 3 forms of the notation. That's the tabular form. So he used 3 different alphabets and up to 6 superscripts around every single part to indicate these various features of it, the kinds of motion, and so on. That is a timing diagram from Difference Engine 2, and for those into such things, the diagonal symmetry here is the pipelining. There's a thing here, that's the odds and evens axis, even differences, odd differences. And each of those symbols actually means something. So this means lift the sector axis. That little arrow with a double head means lift the sector axis 0.34 of an inch. This then means the circular thing there means a rotational motion. That little line means it's additive direction. It's a positive direction. So this thing says then lift the sector 0.34 inches, rotate it for 8 units, from 2 to 10 units of time, and that will return it to the rest position, which is the significance of the double-headed arrow. F means it's free, L means it's locked. So that is a complete description. Over there, that means that you will have an event which is only 1 unit in duration, but it will occur somewhere in that window. So you can see here's an example of how he's trying to capture in abstract form, in symbolic form, the physical motions of the mechanical logic. That is the flow diagram form. So you've got a tabular form, you've got a timing diagram which shows the phasing of the orchestrated movements, and then you've got what he calls the trains, which is the influence of one part of the machine onto another. And you can see the separation of, that's data and that's control. That's the data from the calculating part, the 31 digits. That's the control mechanism which operates the printer. So what we're trying to do, quite in a rather revolutionary way, is see where you can simulate the machine using the hardware description language to inform the simulator, to actually drive the simulation. And that's a research project that we're kind of currently running. That's a close-up of the detail of the last picture I showed you. And there you can see this stops the engine. I mentioned that the printing apparatus, when it got to the end of the page, would automatically halt the machine. And here you can see this stops the engine. That's when the page gets when the thing gets to the end of its line, end of its column, if it's doing line to line, and so on. So, and that's the full device. It's 4,000 parts. So that one single flow diagram actually is an abstract formalization of a 4,000-part apparatus. I'm now going to show you 2 videos. The hard work's done. I'm going to show you a video of how Babbage's locking security systems work. Okay, you've got a figure wheel. You've got a lock. A lock is a thing with a wedge-shaped thing. You can see it here. There's a little wedge. That little shadow is the wedge. So this lock is like a sword blade which runs on the entire column. That wedge goes between the teeth, and the wedge has 3 functions. Firstly, if there's a small derangement, you get, this is what I call pulse shaping. You get automatic error correction. So if it's deranged slightly, it will automatically center because of the entry of the wedge. During periods of the cycle where that thing should not be moved, because it shouldn't move, because it might be deranged, because it might be influenced by something else, but shouldn't be, it locks it and holds the lock in, and that the device can't move. And finally, if a wheel drifts through 2 1/4 degrees, as the lock comes in, it will hit a tooth end on and jam. Now, jamming is not as catastrophic as it might appear. Jamming is a form of error detection. If the machine jams, it's indicating that there's a wheel in an indeterminate position. It's no longer digital. The integrity of the calculation has been compromised, and the machine must jam in order to alert the operator that the results are unreliable. So that's what the lock does, and we can now watch it operate. Okay, these are operating on racks, horizontal racks, not figure wheels. And you can see as it enters, if you just watch there, watch very carefully as it goes in, it automatically readjusts everything so that it's aligned. As it goes in, boom, there's a small deviation. I don't know if you can spot it. Right, it's self-correcting. Now that operates all the way through. It's correcting all the time. Now there are locks throughout the engine. Boom. Okay. So that's one example of how the lock, that's on racks, it's easier to use. Most of them are on figure wheel columns, so the inside you can't see them. That one's done because it's quite exposed. It's part of those are the horizontal racks which communicate from the tabular value to the printer. Okay, I'm going to run the engine for you now. This takes about just over a minute. Unfortunately, the quality isn't massively good because it was actually transferred, it was pre-video days, actually. Okay, that's Richard Horton, Science Museum engineer. Now that slapping sound is the locks coming in. Every one of those columns has a lock. What you can see there is the print roller going up and taking an inked impression of the result. There we go. Boom. Every cycle of the machine. It produces 6 results every minute. Sorry, 10 results every minute, 1 every 6 seconds. Right, that weight drops and advances the paper tray automatically, the matrix tray for the stereotyper. Okay, this is the cam stack. This is the microprogram. This orchestrates the internal functions. That's 28 cams, 14 conjugate cams. Each has a geometric inversion of itself with cam follow. So you can see a cam follower, that's operating the locks. You can hear that slapping sound synchronized to that. The timing cycle is terribly, terribly tight. Right, so it just pans back so you can reorient. Now you can see the shifting motion here is that pipelining I mentioned. We'll see it again now. You can see all the odds move together, all the evens. So 1, 3, 5 moves, and then the evens move together. I mean, who cares whether it works? Okay, this is just pure ballet. This is mechanical ballet. That's the successive carry mechanism working. It's polling each decade in turn to find if there's a carry which needs to be propagated. It's a helical, it's like double DNA, balancing DNA. Okay, what can we conclude from this? How practical, what kind of proposition is it? So very, very briefly. There are several challenges. One is the knowledge gap. 3 people studied these. Okay, the archive, Babbage's archive consists of 1,000 notation, 7,000 sheets of manuscript. Only 3 people have ever studied this, and not completely. And that's Bruce Collier, an American, did a Harvard PhD in 1970, wrote a beautiful thesis on the evolution of Babbage's ideas. Professor Sir Maurice Wilkes, who in 1969, 1974, 1971, the bicentenary, one of the bicentenaries, he did a modern evaluation, the first evaluation in the modern era of Babbage as a computer pioneer. And finally, Alan Bromley, who was the person who really cracked these designs in huge detail, who's produced some masterful papers, and none of those 3 are alive. Bromley died in 2002. He published only 3 papers, which are kind of survey papers. So one is there's a knowledge gap. We're going to have to recover a lot of knowledge that was lost by these 3 people. So one of the things we want to build in is succession planning. So we want a bunch of postdocs in there, so that if this thing's going to take 170 years, we're going to need some continuity. So one is the knowledge gap. There are 2 forms of knowledge. One is the lost knowledge that people have already had. The other thing is the knowledge gap in the sense that there is no complete drawing. We're behind the starting line. With Difference Engine 2, we had 20 complete sets of drawings as a starting point. Over here, you've got 3 different versions of the machine, incompletely specified. There are some elements of one version specified in great detail and elements of another detail which are missing completely. It is not entirely clear how the control mechanisms to integrate the high-level control from punch cards with the microprogram internally. How do you program the thing for multiple processing? It's not evident that Babbage actually worked this out in any huge detail. So there's a knowledge gap. We're behind the starting line there. So those sort of things darken our prospects. What brightens our prospects? What brightens our prospects is the fact that we started the Difference Engine 2 project in 1985. We finished the first engine in 2002. And then we built a duplicate, a multiple original for Nathan Mervold for his private collection in California. And that's the one that's now currently on exhibition at the Computer History Museum in California. We used conventional pen and paper design for all the parts. The 168 drawings are drawn by hand using a conventional draftsman. That was a huge overhead in resources, in physical time and in resources. The biggest single thing, which will collapse our 170 years to what I estimate will be substantially less, is we're going to simulate the machine before we even build it. And I would suggest that we can actually solve almost all, certainly issues of logical feasibility, completeness, all except the final engineering issues done at stage of simulation. Also, if the simulation front end is chosen judiciously as a front end to a CAD-CAM system, manufacturing then ceases to be the huge burden it was when we had to do things by hand fettling and so on. So, so if we put all this in a kind of predictive mix and mix together the classic and traditional engineering fudge factors, guesswork, divination, astrological prediction. I reckon on 15 to 20 years to construct and between 20 and $40 million. And so I would put the question mark in Mission Impossible. Thanks very much.
Doron, I'll let you steer them.
So when you built the different section, how many bugs did you find in the design?
There are two categories of, you're talking about deficiencies in the drawings or actually trying to debug the thing in real life?
No, I'm talking about the plan.
The plans. There are two.
You can talk about the other two.
The plans provide a complete logical description of what the machine's intended to do and what the parts, shape of the parts were. What it does not contain is methods of manufacture, which it couldn't do, choice of materials, finish, and tolerancing, because tolerancing didn't exist in those days. There were no interchangeable parts. You couldn't say, make a part in a tolerance. We had to provide all that from modern manufacturing terms. So that information is missing. But in terms of bugs, we found, astonishingly, no fundamental logical errors that compromised the fundamental function of the machine. There were a huge number of things, thousands of things we had to do to make it work, but none of them were logical things. There's only one device we actually had to redesign. And that was not a logical device. It was a sliding clutch in the print mechanism where you had a drive mechanism that was sliding in a slot on a shaft and had to turn at the same time. And the load, the torque on that part made it such that it couldn't slide. So we redesigned that part in the same space. That's the most extreme redesign we had to do. Not a logical thing, a practical thing about just a pure engineering thing. There were a huge number of modifications we had to do. For instance, when you turn, you saw that cam follower with that slapping sound hitting that steep rise. You couldn't turn the handle to get the cam follower past that rise. So wherever there were modifications to be made, we looked elsewhere for solutions Babbage had used. And Babbage had used a counterbalancing spring. Those axes actually aren't displaced up and down. They bob around a neutral position and are just displaced because they counterbalance from on top. So you don't actually carry the load of turning that handle to lift that ton of all those axes. So we used the same technique, slotted it underneath, and lo and behold. So there's an example of a modification which I would say is inessential in logical terms. We found, in short, there was nothing that compromised the logical validity of this machine that we had to do, but there were thousands of engineering instances. We strengthened framing. We had to increase tolerances to make clearances where there were no clearances. We had to resolve issues in the... There's one terrible error in the drawings, which is so basic, it's incomprehensible that it might not have been deliberate. And that is the fundamental carry mechanism doesn't work as drawn, but a mirror image of it does, because the direction of rotation is wrong. And there's speculation whether this was to prevent industrial espionage or the draftsman got it wrong. But their example, a mirror image, the fundamental workings of the thing. There were precautionary modifications, there were remedial modifications. Precautionary modifications are things we anticipated. We didn't think that the weight of the printer was well supported on the frame, so we built bigger brackets. That was a remedial one. There were precautionary ones where we thought that there was one tooth on an impact gear that would come under particular stress. And so we used a slightly higher grade of steel, only part in the whole machine that we used a slightly higher grade of steel than Babbage himself would have had available. But for the rest, the bronze, the cast iron, and the steels, we did composition analysis on these things to match the metals as precisely as we could. And we built the machine no more precisely than we know from measurement from difference engine 1, Babbage himself could have achieved. And that was the idea. We had to resist the charge that says you built it, but Babbage could not have. Otherwise, we would have indicated nothing if we'd actually used modern techniques. We didn't use period manufacturing. We used CAD-CAM system. We used computer-aided manufacture, but always within tolerances, preferably sloppier than actually Babbage. So in short, there were huge numbers of discrepancies. Like, for instance, the same part represented inconsistently on two views of the same. So the same part we dimensioned differently between two drawings. Well, you can't build it as Babbage designed with a problem like that. There are omissions. There are omitted mechanisms. The printing mechanism has print wheels and inking rollers with no visible means of support. They just sit there. Either it was incomplete or we thought it's so trivial to derive the drive from somewhere else, so that's what we did. But always looking for solutions that Babbage had used elsewhere. So in short, no fundamental logical difficulties, huge numbers of engineering issues.
similar vein, you mentioned that the analytical engine isn't really completely described, probably more so than the difference engine.
Yes.
So, do you think it actually works the way it's supposed to? Like, do you think that something like that would actually work?
I'll tell you why there's cause for optimism. The printing mechanism that I showed you is designed for the analytical engine and the difference engine. It's a dual design. Because that's the most sophisticated. 1846, he stopped the analytical engine. Came back to it later with some refinements. 1846. He designed difference engine 2 between 1847 and 1849, immediately after this. So this was, he's fresh from the analytical engine. He wants a printer for the analytical engine. He designs a dual-purpose one. So we built a piece. We built 4,000 parts of the analytical engine. And it's spectacular. It works as exactly as intended. So I think the incompletenesses are things that are resolvable by immersing oneself in the design style and the thinking. But the incompletenesses are substantial.
Because the list of features that you mentioned, I mean, it's not unlike, you know, the first computers that were actually big, significant.
Yes.
So
Yes. No, nothing new. Yes.
well, it's quite amazing.
Yes. So, you know, we have reasons for confidence, you know, that until we built the engine, there was an historical question mark over Babbage. Babbage's guy designed these huge, vast mechanical engines, but he never built them. And the big question was, with the circumstances surrounding the collapse of his own attempts to do so, did that conceal the logical or technical impossibility of the machines? So a question mark is always hung over his head in the sense of, was this an impractical dreamer or a genius designer? And the fact that his engine works as he intended it to work, and we used parts with no greater precision than was achievable in his day, sort of pretty well vindicates the fact that we're talking about some, you know, vision verging on genius here. We're talking about somebody who was not just a visionary, but somebody who actually was a designer of extraordinary caliber. So those are reasons for optimism. Yeah.
In the video, where we see the gentleman cranking the handle and the machine working, and he doesn't seem to be putting in any extraordinary effort, so it seems like the machine is well designed for the kind of energy load that could be produced in that, or supplied in that manner. I'm wondering whether there was any doubt about whether that would turn out that way, whether there were concerns either because of the weight of all the parts that had to move, or because of, well, you mentioned one friction issue having to do with the cams. Were there any other questions relating to friction from having so many parts being moved by just one handle?
I'm tracking back to that elevation. When engineers first looked at this drawing, we were appalled by this. They said you couldn't possibly turn the handle because of cumulative friction. Because the understanding was that each of these columns would drive the column alongside. Here's an example of sorry, this is a digression. You can see there that the gap between that column and that column is bigger than all the others. My question is that significant? It's an error in the drawing. The draftsman started on Monday at this end, started on Thursday at this end, and came there and found there was a gap and said, the hell was this, I'm leaving it. We pondered long and hard whether there was some deep significance to that alteration of pitch. But there's an example of something that had to be resolved, you know, of gaps in the drawing. The question of, right, when engineers first looked at this, they said you couldn't possibly turn the handle. And of course, you know, us Babbage advocates thought, you know, our genius hero could not have made an error so fundamental. You are lifting a huge amount of weight there. And what we did, as a precautionary measure, in deference to the people who doubted that the handle could be turned, we put a 4-to-1 reduction gear in there. So it's 4 times easier to turn the machine and runs 4 times faster. You have to turn it 4 times faster to make it go as Babbage intended. So I'll run on to I'll show you okay, if we just look at this drawing, the handle comes straight out of the main shaft there. Yep, there's the main drive shaft, goes by a bunch of bevel gears down the cam stack, but it's on a line with that shaft. If we go back to the elevation of the machine, you can see the handle actually doesn't come out, the handle doesn't come out of the main shaft, the handle comes down below. And that's a precautionary modification to include the 4-to-1 reduction gear. It's not necessary, but we've never taken it away. We're so happy when it works, we don't touch it. So we've always run it that way, but everything is reversible. You just pull a pin out and you can put the handle back where Babbage intended. The question of issue and friction, the machine is well run in, and as you correctly observed, it's quite easy to turn. You can turn it with one hand. But at 3 or 4 points in the cycle, there's a shock load. When that steep rise on the cam for the locks comes in, you suddenly get a shock load. So there's a trick, there's a technique for running the engine evenly, and that is not to go faster when it's easy, but actually to put some force and to do it very uniformly but strongly, so that you drive it through the shock loads at an even pace. Otherwise it tends to jam. So as far as friction goes, there was a catastrophic piece of frictional difficulty that took us over a year to solve, and it delayed the completion of the printer by a year. And that is that I need this time up. No. I've got a simulation that will demonstrate it easily. These are vertical racks. So there's a gear wheel sitting on the last column which turns this way. You have to transfer that motion to a print wheel going this way. It's done through a series of spindles and vertical racks. So a vertical rack is a thin slice of a slat with gears on it, which is turned by a spindle on top and operates the wheel, the figure wheel at the bottom. Because those are so thin, and they have to fit within the pitch of the printing mechanism, so they have to all fit within the width of one column. That has to fit within the width of one column. There are 30 of those. We thought that because they're so thin, we'd help them by letting them butt onto each other and slide against each other so they'd reinforce each other. That cost us a year, that decision, because the sliding friction was so great, there was a back pressure which started distorting and affecting the timing of the rest of the machine. We didn't understand that. We started solving the problems that were consequential on this decision. So we used all kinds of things. We put an electric motor on to wear them in and ran them for 36 hours to try and wear the vertical racks in. We then used conventional oils, catastrophic. Surface tension meant they actually stuck together. We dried them all out. We used graphite. And eventually we said, take these out and reduce the bearing surfaces by machining, scalloping out pieces to reduce the bearing, and thin the whole lot completely. So the actual thing. And you can actually see air through them now. They're quite strong enough, and that solved the problem. But that was the only frictional problem. It's not inherent to Babbage's design. It's because we chose. He doesn't specify tolerances. And so we, as a precautionary measure, said we'll reinforce these slats by butting them onto each other, and that was catastrophic. It masked a huge number of, it created a huge number of problems, and the problems of which masked the actual cause. But that's the only frictional issue that there was.
All right, I think let's let Doron surrender.